All right. Okay, everybody, let's get started. My apologies for being a couple minutes late. I had a conference call that I was on. Part of my duties as your associate dean. It just went over a little bit. My apologies. First off, hope everybody had a relaxing Thanksgiving break. If you saw either the video that was posted on Teams or your email inbox this morning, exam number 3 has been graded. Okay. Now I'm going to spend the first little bit of this lecture talking about some housekeeping for the end of this course, because that's where we're at. This is it. This is our last week in Engineering 213. So we're going to do a little bit of housekeeping. One of the housekeeping items that I posted to Teams last night was the at-home game. Did everybody see that post? So what that will do is there are 5 like orange cells, and those orange cells are for your attendance grade, your homework, and the first 3 exams. If you input your grades currently on Blackboard for those 5 items, what it will do is, first off, it will tell you what your current grade is, which should match what's on Blackboard right now, and then it will back calculate what you need to get on the exam to get an A, get a B, get a C, whatever. A couple points worth mentioning. Number 1, we obviously still have a little bit to do this week, so those numbers might slightly change, with attendance grades and whatnot. 2, it is back calculating that based off of rounded grades. So for example, I round grades at the end. So if you get an 89.7, I round that up to an A. So it's back calculating what you need to get on the final to earn an 89.5 or a 79.5 or a 69.5. It's not doing it for a 70, and so on and so forth. Has everybody seen that? Does anybody have any questions about the at-home game? When I was in grad school, a buddy of mine called that where he back calculate what he needed to get on the final. He called that playing the at-home game. That's why I called the spreadsheet that. Has everybody used it? Does anybody have any questions about it? Okay. All right. Before we begin our last lecture, which is really just sort of closing the loop on friction, I want to talk about some remaining housekeeping items for this class. And I know that your primary concern is understanding what your grade's going to be at the end of the day. Secondary is, that whole learning thing. That was a joke, not a very funny one. But let's talk about, in all seriousness, let's talk about remaining housekeeping items for the class. So first off, attendance grades. Attendance is graded in this course, and all the attendance up till today is current and up to date on Blackboard. We obviously have 3 more lectures, so if you have perfect attendance and you keep coming to class this week, that grade's not going to change. But, if you missed a few days and you show up every day this week, that grade's just going to go up. So that's going to get updated, and I'm going to try and do that every day, Monday, Wednesday, and Friday this week so that it's current. Homework assignments. Okay, so all the homeworks up to homework 6.2 are graded. 6.3 and 6.4 are currently being graded. Okay, my TAs, hopefully they don't have a whole lot more to do on 6.3 and 6.4, and I think even for 6.3 and 6.4, some of those are graded. I'll turn those visible when they're all graded. But that should be done relatively quickly. You do have one more homework assignment, which is the homework assignment on friction, which is due on Wednesday, and that's it for standard homework assignments. I do have one more assignment, which is going to be a bonus assignment. What I'm going to do is I'm going to ask you to fill out your course evals. I take your comments very seriously. This is only my second time teaching this course. It's my first time teaching it in person, and it is also my first time teaching a class this big. I've never really had, I've taught Engineering 103, but that's not the same thing as this. So I do take your feedback rather seriously. And again, you can put me through the ringer if you want. You can say that my math jokes are horrible and I need to derive some new ones. But I do want you to do it. And if you do it and upload proof that you've done it, I don't want to see what you wrote. I just want to see that you did it. You can just upload a screenshot of your completed survey list. I will give you 10 bonus points on top of your homework average. You know how each homework is worth 10 points. That'll just sort of be another free point. So Can you theoretically get a homework average over 100%? Yes, you can. I have no problem with that. So that will open up Wednesday. I want you to spend between now and Wednesday focusing on friction. I'm going to close that assignment on Monday. The survey, I think, actually closes on Friday. But I'm going to open that on Wednesday. I had one or two of you just email me the screenshot, and I appreciate that. But I really would ask that once this opens on Wednesday that you upload it, or I'm going to lose it. There's so many people in here, I want to make sure that I keep track of it. All right, some remaining housekeeping. So our remaining lecture schedule, this is what we're going to do for this week. Today, we're going to continue and finalize our discussion on friction. So I have one more problem that I want to do with you on friction, and really the only additional parameter is the inclusion of trig. I'm going to take the block that Yoshi was trying to push and put it on an incline, basically, and just see what happens. What we're going to do on Wednesday is a comprehensive course review, and it's basically going to be like what I did for exam 1 review, exam 2 review, exam 3 review, but I'm going to do it for everything. I'm going to talk about everything that's going to be on the exam because the exam is comprehensive. And we'll begin the process of maybe answering some of your questions that you might have about what's going to be on the final. But for Friday is basically going to be me just coming in and answering questions about the final. That's kind of all I want to do on Friday. For the final will be on Friday, December 10th. We drew the short straw for this class because it's the last day, the last time slot, which means I have 60 exams to grade by that Monday.
There is an easier way to get around that, right? So again, I like going 100.
We teach children. We teach children the difference between what is right and what is wrong, but the real challenge is what is right and what is easy. So.
But every once in a while, you get somebody a C, and it looks like it's right.
I'm going to move past that comment because I don't have a response. Oh, yeah, you all would say that. He's not wrong, yeah. All right. The exam is going to be of similar logistics and operation of previous exams, but it's a 2-hour exam, so it's going to be a 2-hour exam. It's comprehensive. It's going to include friction, so there's going to be, I'm going to tell you, there is one friction problem. Let me address one question I got on Teams, and I'll just be blunt for the reason that I'm not able to do it right now. There was a question about whether or not would I make the exam problems available for study, and I have no problem with that at all. I really don't. What I'll do is I will post the problems and I'll post the answers. What I'm not going to post are the worked out solutions, not because I have some intellectual property reason for holding them back, but you kind of need to work through them. You kind of need to do the work to study. So I will do that. And to be blunt, the reason why I haven't posted them yet is because I still have some students who need to do some makeup exams because they weren't able to take them. Once that's done, they're all posted. Okay, is that fair? Okay, and that should be done hopefully soon or early this week. So what I can go ahead and do, I just didn't have time, is exam 1. I can go ahead and post that now. So I will happily do that. What I'll do is I'll post the computational problems and those answers, and then you should be able to work through that. One thing that did surprise me for exam 1 is how many of you did not pick up your work for exam 1. And maybe I had a spring of kindness in my heart. I told you I was getting rid of them after the first week, and I ended up sticking them in a drawer, so I still have them. What I will do is I will happily bring them on Wednesday. The exam 3 is outside my office right now, just like the last 2 exams, so if you could grab it, I would appreciate it. But I also have your exam 1s ready as well. Is that fair? All right. Any questions about housekeeping for Engineering 213? Any questions? Okay. So I would like to, excuse me, goodness. It's what happens when I talk too much. I would like to begin our last topic lecture of the course which is to finish our coverage of static and kinetic friction. So I want you to recall the two forces that we are interested in characterizing and categorizing in friction situations. In other words, when we have two objects in direct contact and their potential to slide across one another. And that is the force required to begin motion, which is what we're calling F sub m, which is the product of the normal force and the coefficient of static friction, and then the force that's generated during motion. Now remember, F sub m is always bigger than F sub k because the coefficient of static friction is always bigger than the coefficient of kinetic friction. And the way that it works is if I have this object that I want to push across the floor, let's say this table, I want to push it across the floor, that floor will resist that motion up until that force exceeds F sub m. Once that force exceeds F sub m and the object begins moving, I will develop a constant resisting force of F sub k. Does that make sense? So if you were to plot that, you'd have an x and y axis, and your resisting force would sort of go up like this to F sub m, and then once you hit F sub m, bam, it suddenly decreases to F sub k, something like that. And there was a plot like that earlier in an earlier slide in lecture 35, I think it was. One other thing I'll mention. All of the slides are now on Blackboard, all of them, so the entire semester. So the coefficient of kinetic friction is always smaller than the coefficient of static friction. A rule of thumb is that the coefficient of kinetic friction is about 75% of the coefficient of static friction. That's not always the case. Sometimes it's 80%, sometimes it's 60%, but categorizing every permutation of contact you could think of, that's a good average. So now both the force required to generate, or the force required to achieve motion and the forces generated during motion, both of those are functions of the normal force. And what the normal force is the force that is resisted or is being supplied by the plane in question. If I have two objects in contact, the normal force is the sum of all the normal components between those two objects. Now, what we didn't have to deal with last time was the object being at an incline, but very possibly that is a realistic situation that we have to deal with in the world of statics. So, for example, because I don't want to spill all of my electronics and whatnot here that's on this table, here I have this table, and I've got, let's use two objects. Let's use this, and let's use this. Okay? Now, both of these objects have different weights. So because they have different weights, they're going to have different normal forces. But what's also more interesting is not just the normal force, but the coefficient of friction. If I take this table and I pick it up on an incline, what I'm doing is I'm taking the force generated by these objects due to their weight, and I'm splitting them up into x and y components. X being, we'll say, parallel to the plane of the table, and y being perpendicular to the plane of the table. Now, right now, if you look at the way the table is right now, the entire component of weight is acting perpendicular to the table. So like the y component is the weight, and the x component is 0. As I take this table and I put it on an incline, now some of that weight is being directed down the incline, right? And as it makes sense, the more that I take this table and lift it up, the more of that weight is being directed along the plane of the table, and once that force exceeds F sub m, boom, it slides. Okay? Now, why did this fall and the tape dispenser not fall? And think, this is heavier. This should have fallen first if it wasn't for something else. Its coefficient of friction is higher. Here we have this rubber gasket. This is like if you go to I don't know if any of you have like a vehicle and you have that little pad on your dashboard to where if you stick your phone on, it won't slide. You know, that's kind of what this material is. That material has a very high coefficient of friction because we don't want it to move, right? With this has a much higher coefficient of friction than this does. Does this make sense? Okay. Now, when you're dealing with inclined surfaces, you're going to use some trig to split it up into X and Y components. There's a lot here on this slide about, and this is really for the mathematical purists in the room that recognize that if I take this object and split it up into its X and Y components, when I'm looking at the normal components of that force, I have to flip my slope ratios. But really, I just want you to use a little bit of common sense. So, for example, here's the tape dispenser. Let's just use the tape dispenser as an example. Now, let's say that this tape dispenser weighs 5 pounds, okay? So the tape dispenser's on the table. It weighs 5 pounds. I propose that right now, the angle of incline is 0, right? So the Y component we'll say is 5 pounds, and the X component is 0. X being this way, Y being perpendicular to the table. Now, if I take this and lift it a little bit, let's just make it up and say I lifted it up like an incline of 3 degrees, right? I can do the X and Y components of that using cosine and sine. And what will probably happen is, depending upon which order that I do it, and whether I use 3 degrees or I use 87 degrees, it doesn't matter. I'm going to get that one of those components is like 4.95 and the other's like, I don't know, 0.2. Does that make sense? If you take this 5 pounds and split it up into X and Y components based on an angle of 3 degrees. Does that make sense? Now, if I do that, would you agree that the 4.95, the bigger component, is pointing towards the table? And the smaller component, maybe the 0.2 pounds, is pointing that way, right? As the angle increases, though, if I were to flip the script and take this table and move it like that, where it was maybe like 87 degrees up, very little of it is going into the table. The whole point is just use a little bit of common sense when you're identifying which component goes in which direction, and you'll find that these problems are very, very straightforward. In order to do that, I want to illustrate what's going on with this particular example. So I have a 300-pound crate, and this 300-pound crate is on an incline that has a 3-to-4 slope ratio. So you can do this however you want. If you want to do the trig to get the angle and sines and cosines, that's fine. We might go ahead and do that in here just so that we're familiar with that. However, because this is a 3, 4, 5 triangle, I will tell you that the X and Y components of this 300 pounds are going to be neat whole numbers. Okay? Now, I have this 300-pound crate that's on an incline, and because it's on an incline, it has a tendency to want to slide down the incline. Well, there's a 100-pound force pushing it up the incline. My question is, what's going on? Is the box going to sit still? Is it going to slide down the incline? Is it going to move up the incline? What is the deal? Okay? Determine whether or not the crate is in equilibrium and find the value of the frictional force. How much friction is being developed between these two planes? If you understood the riddles, if you will, the Yoshi riddles that we did last time, you're going to find this is very straightforward. And if you understand this, not only will your homework assignment be a breeze, but I do have a strong feeling that your exam problem related to friction will be a breeze. All right. All right, I need to screen capture this because I haven't done it. Okay, so we have a 100-pound force being applied to a 300-pound crate. One of the things I want to do right off the bat is I want to identify what I'm considering to be my X and Y axes. So typically when I do these problems, what I like to do is I like to say that the x-axis goes along the direction of the incline and the y-axis is perpendicular or normal to the incline. So whenever I'm determining my normal force, I'm going to be looking at my components along the y direction. Does that make sense? And again, if you use a little bit of common sense, I think you're going to find this is very straightforward. Okay, so the first thing I want to do is I want to take this 300-pound load and I want to split it up into its x and y components. And by x and y components, I'm talking about this coordinate system. Notice that I don't need to do that with this 100-pound load here because it's already acting along the x direction that I've defined. And so the way that I'm going to do that is, again, I'm going to be very, very simple with it. Okay, so and say you can do this however you want. If you want to use the slope ratios, you want to use trig, that's fine. Let's use the trig approach just to make sure that we're comfortable with it. So the trig approach is finding this angle. So I propose that the tangent of that angle is defined as 3/4. So that angle is the inverse tangent of that. And what is the inverse tangent of 3/4? I know we just got back from the turkey break, but every engineering student should have their Casio FX115 ES Plus or equivalent scientific calculator with them, even during dead week. $36.87 degrees. So this ramp is at an incline of 36.87 degrees. So I propose that when I split this up into the x and y components, the bigger component should go along the y-axis. Would that be a fair statement? Okay, so if I take 300 pounds times the cosine of 36.87 degrees and 300 pounds times the sine of 36.87 degrees. So what do we get for the first one? What's 300 pounds times the cosine of 36.87 degrees? If I was a betting man, I was going to say, I bet you it's 240 pounds. And what's this next one? It's 180. Why are these such neat, pretty, nice numbers? Because it's a 3, 4, 5 triangle, right? You could say that the x component and the y component are just 4/5 and 3/5, whichever one made sense, right? Because it's, again, cosine and sine, opposite over hypotenuse, adjacent over hypotenuse. Now, what I am proposing is this for the weight of that crate. So here's the crate. And here's the y-axis, here's the x-axis. Now remember, we have this 100-pound load acting like this. What we need to do is we need to take this weight of the crate and split it up into an x and y component. Let's just use a little bit of common sense, okay? Here's the crate. If I take this along an incline, which way is the x component going to act? Is it going to act down or up? Down, right? Because it wants to slide down, right? So I propose that the x component needs to act like that. The y component is still acting this way. Why is it acting that way and not up? Because if it was acting up, the tape dispenser or the crate would be flying into the ceiling, right? Does that make sense? Okay. Now, as for their magnitudes, here's what I propose. This incline is less than 45 degrees. Again, take my x and y components, and let's say they were like, instead of 240 and 180, let's say they were like 290 and 15. That would mean that it's only like this. I would propose that most of that force is going in the y direction and less is going in the x direction. And the reason is because that incline is less than 45 degrees. I propose that Wx is the 180 and Wy is the 240. And we're sort of flipping the script here. We're saying that the x component is associated with the sine, the y component is associated with the cosine. Why? Because we're basically talking about perpendicular planes. Remember, if you have a line, how do you determine the slope of a line perpendicular to it? You flip the slope. That's what we're doing here. So I propose this is 180. This is 240. Is that a fair statement? Everybody okay with that? So if you're okay with that, what I want to do is take this free body diagram. I want to simplify it a little bit. And this seems like a superfluous step, but I promise it's not so superfluous on your homework assignment. I'd like to think about this maybe in terms of resultants. So let's look at the x direction. Let's look at the x direction. So I have 180 pounds going down the slope and only 100 pounds going up the slope. So I propose that if I was trying to find the resultant of forces acting on the crate, that the resultant force would be Rx is 80 pounds. Does that make sense? In other words, the crate's own weight is causing it to want to slide down the ramp with a force of 180 pounds. The problem is that we are only pushing up with a force of 100 pounds. So there's a differential, and the differential is 80 pounds. Does that make sense? So is this force enough to push the crate back up the ramp? No, of course not. We need a lot more force to consider pushing it up the ramp, because not only would we need to exceed 180, but we would need to exceed the friction developed between these two planes. Speaking of the friction, we only have one vertical force. So I'll call that Ry is 240 pounds. So if you're wondering what I'm doing, I'm taking the forces on the system and determining their resultant. The resultant in the x direction, the resultant in the y direction. Why? Because I'm trying to figure out two things right now. Is this crate flying off into space or sinking into the ramp? No, because if the crate is pushing down into the ramp with a force of 240 pounds, the ramp is responding with a normal force of 240 pounds. That's the normal force, okay? And it's pretty easy, like couldn't you have figured that out from here? Like 240 down, 240 pound up? Yeah, but with your homework assignment, this 100 pounds is also at an angle. So it's advantageous to take this and do this exercise. Now, I propose that there's also another force I'm forgetting, which is the whole point of the problem, the frictional force. Which direction does friction always act? Whenever you apply force to an object, which way does what does friction do? Exactly. If I push this table that way, friction's acting this way. That's physics. This block, this crate, is tending to want to slide down the ramp. The friction is going to act to resist that. Does that make sense? Now, what we haven't figured out is if the crate's in equilibrium or not. Is it going to move or is it going to sit still? How do we do that? How do we figure out whether or not the crate's going to sit still or whether or not it's going to move? I'm asking you. How do we determine if two objects in contact are going to move? Well, it's whether or not we've exceeded Fm, the force required to generate motion. Maybe we ought to compute that. What is the force required to begin motion? That's Fm. And how do we compute? Oh, that's a horrible one. I can do better than that. That is mu sub s times n. What was mu sub s for this problem? What were the coefficients? 0.25 and 0.2. So what is 0.25 of 240 pounds? What's that, 60? Everybody okay with the math? Now let me ask you a question. Based on what you're looking at right now on the screen, is that crate going to sit still or is it going to move? Who votes sit still? Who votes move? Good. It's moving. Why is it moving? Because Rx is bigger than that. The crate wants to tend down the ramp with a force of 80 pounds. And I need to exceed 60 pounds to begin motion. So is it going to move? Yeah, it's going to move. So I'll say Rx greater than Fm, crate is in motion. Now, if the crate is in motion, what is F sub F?
N times mu k minus, or the difference between the force of kinetic friction and
Nope. You're making it more complicated. Look, here's the crate. Crate's moving. How much force is resisting the crate moving? It's simpler than that. It's exactly right. It's just Fk. It's just mu Kn. See, because the crate is in motion, how much friction is developed? The friction developed during motion. Therefore, the friction is just this. So you're thinking about this, trying to say, is it in equilibrium? It's not in equilibrium because it's moving. We're outside statics land at this point. We finally entered the realm of dynamics. So what's the answer to this problem? Crate is not in equilibrium. FF is 48 pounds. Now I'm going to stop for a second, see if, did that make sense? How about everybody else? Is there anything about this example that's fuzzy? Because friction's one of those things in this course that probably more than anything feels like a riddle. You know, you've got to like look at the forces and go, okay, which way is it going to move? Is it, you know, and so on and so forth. Anybody have any questions? Okay, let's talk about some housekeeping, and then I'm going to let you go early. So what I'll do today is post exam 1 to Teams. You have a homework 7 that's due Wednesday. One thing I do want to mention, there's 58 students in here, and I've only had, I think, 1 student comment on the thread for questions for the final. If you've got questions, ask them. We've got all of, I'm going to go through the topics on the final on Wednesday, but we've got some of Wednesday and all of Friday to talk about Engineering 213 for the final. If you got questions, please ask them. Don't forget your course evals, but we've got 2 lectures left, but that's actually it for the topics in this course. I will see you on Wednesday. Your homework's due. Have fun studying. That's all I got.